Hello and welcome everyone. Today we'll be looking at a basic op-amp circuit. This is problem 623 from Engineering Circuit Analysis by William H. Haidt. Now, we know a few things right off the bat looking at the circuit from the ideals of an op-amp. We know that there's no current going through the op-amp and that the voltage across these two terminals is zero. So let's say we have V sub positive, which is representing the positive terminal of the op amp. That is equal to V sub negative, which we'll say V sub n. And by the definition, there should be no change, therefore they're equal. We also know that there is no current going through this op amp right here. And therefore, if there's no current going through this, there can't be any current going through this resistor right here. So if we write that out, the equation I sub 1 mega ohm resistor, the current is equal to 0, which is equal to V sub p minus 0 over 1 mega ohm. V sub p would be right here. I guess I can't really draw it in there. But from this equation, we can also see, therefore, that V sub p must also equal 0. And therefore, up in this equation, we know that both of these is equal to 0. And that will help us significantly in determining our node equation at node A, which in return will allow us to find the voltage here. We'll call this V sub plus and V sub minus. So we know that V sub x is equal to V sub plus minus V sub minus. It's just the voltage across there. Very basic stuff. Alright, so why don't we look at node A? We have node A, and then let's do our KCL equations. For current, we have the current from here. We have the current from this 100k ohm resistor, and then we have some current going out, but we know that outbound current is equal to 0, so we can right away write 0 is equal to, let's label this I1 and I2. I1 plus I2. Now right away you can see why this is called an inverting amplifier, because when we rearrange the equation, we have I1 is equal to negative I2. Now the question is, what are those? And one other little tricky thing in here is we have a current source instead of a voltage source. However, luckily the problem set it up perfectly for us to convert this using source transformation into a Thevenin voltage source. So let's do that over here. We have a 3 milliamp source, so our current is equal to 3 milliamps. And we know that our R sub Thevenin is equal to 1 kilo ohm. So using Ohm's law, we know that the voltage would equal 3 volts. However, the arrow's pointing in the opposite direction of our current, so why don't we make this a negative, and then we can reverse it. So redrawing the circuit right over there, we'd have our ground going up into a voltage source. Now normally these signs should be the other way, however we reverse the output, so it's okay to draw it as this. And then we have our resistor, 1 kilo ohm, right here. And that'd be the terminal at A. So using that, we can help us calculate this V sub plus right here. So back to our node equation right here, let's finish that up. 0 is equal to I1, okay, never mind. Let's get rid of that. Let's see if we can get this to work. All right. Let's use this equation right here. I1 is equal to negative I2. So I1 is right here. So negative 3 minus our nodal voltage at A, which we already know is 0, because it's the same as V negative, which is the same as V positive, which is all equal to 0. Now let's put that over our resistance, which is 1 kilo ohm. And that is equal to negative the quantity of V sub plus minus 0, which is also V sub A or V sub N or V sub P, over our resistance, which is 100 kilo ohms. Okay, so now we can solve for V sub P, and that'll end up equaling 14.29 volts. You can work that out on your calculator, and to solve it, you just use basic algebra. Now let's look at the right-hand side of our equation, or of our circuit, I should say. That is much easier. We don't have to do any source transformation, and we already proved earlier that the voltage across this is 0 since there is no current going through it. So let's do our node equation. We'd still again have the I2 is equal to negative I1. Well, that's actually backwards, but who cares? We'll just do it that way. So this, we'll call this our I2, and this will be our I1. And so we have V sub minus 0, which is our nodal voltage at B, over our resistance, which is 100 ohms, is equal to negative quantity of 5 volts minus 0 over our resistance, which is 10. And if you work that out, you should get V sub minus equal to 50. Now I know I'm jumping around a lot, but let's jump right back up here. Now that we have these two quantities right here and right here, we can plug those into our last equation. So we have, oops, and this should be a negative because remember the quantity is negative. So we have 14.29 volts minus a minus 50, which is the equivalent of adding it, which is equal to 64.29 volts. And there you go. That is our voltage across V sub x.